stop recording. So the topic is about transformers, devices that transform voltage and current. Obviously, these are not transformers that live on the other side of the moon, right? Don't get confused. So what is a transformer like in terms of like physical features? So basically you have sheets of metal glued together. Usually it's iron based because you need to have material that would amplify the magnetic field. So you have multiple sheets of iron glued together with non-conductive glue, right? And they're really thin sheets of metal, so it means they have high resistance. And they would, you try to avoid all kinds of eddy currents going inside this core. And what you do is you surround this with a coil, a wire. Usually it's copper wire, right? And usually hundreds of turns, but we're gonna just use a few turns. So that is already a transformer, but it's not gonna work because it needs a secondary coil. So we'll show that a little bit later. Let's just consider what happens if we provide this with changing voltage. So this symbol tilde means changing voltage. So for the first part, we're going to consider the voltage is going to be increasing. So this is going to be voltage on the primary coil, VP. So question to all of you, what happens to the current in the primary coil as we increase the voltage? So increasing voltage leads to change of the primary core, the current, right? So what happens to the change in current? Everybody be active. So the current will go up, right? Primary coil, current goes up. Now, what does that lead to? If we're increasing the current in the coil, the next stage. I'm listening, reading your responses. If you increase the current in the coils in this coil, what happens next? So it creates secondary field. Okay, not yet. That's like a little bit later. When we have electric current, what does it create? Electric current, just electric current. What does it create? It creates magnetic field. You guys have to be specific. Magnetic field, magnetic, primary magnetic field in this case. So we'll have like B, primary, which will also be increasing since we're increasing the current, the primary magnetic field will be increasing. What does that lead to? If we're increasing the primary field, what else are we increasing? People be active. Some of you like fall asleep and then forget to like later to log out, which is amazing. So the flux, primary flux will be changing. Now for this specific purposes, we're gonna use the change of the voltage will be following the sine or cosine function. So from there, we can say the change of the flux will also be changing over time. So let's say we're going to be increasing the flux here. Okay, and that's the end of it. Like if you stop here, that's the end of it. What's going to happen here, basically, if you ignore everything else, this will emit electromagnetic waves, like really weak radio waves outward in these two directions, right? But that's not what we're trying to do. We're trying to make a transformer. To make a transformer, you will need to connect this end with another end with a secondary coil, right? Secondary coil will be looking somewhat like this. So again, made of the same kind of stuff, multiple sheets of iron glued together, right? And then wrapped around with a copper wire. So it's going to come here, around, 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 and like that. Okay, so now we can go a little bit further. Changing flux, what does it create in turn? Changing primary flux, what does it create?
Yeah, the secondary field.
Well, basically it creates, first of all, EMF, right? EMF, so EMF. And again, due to the change of the flux, the character of the change of flux, EMF will also be changing. I'm gonna write arrow up. It could be down, it doesn't matter, but basically up means it's increasing in magnitude, but it will carry the negative sign, right? That is equivalent to voltage, so we can actually say that's gonna be voltage. Right? And we can say that's going to be actually equivalent to V secondary voltage, or voltage on the secondary coil, which will be increasing, obviously, right? And then what does that lead to? Last step. So voltage is increasing over time. What does it lead to? Current. So current in the secondary coil will also be increasing. However, keep in mind there will be minus sign, right? So I'm going to put the minus sign here, minus sign here. So what this means is that if voltage on the primary goes up positive, right, then the voltage in secondary will go lower, like in the negative. So it will increase in the negative direction. So there's that shift there. Okay. So Dean, if you keep your mic off, please. Now, if the secondary coil is absent, it will still be EMF. So we can actually draw that as like a branch coming off. So there will be change of the electric field. Electric field will be changing over time. This is electric field, remember that, it's not EMF. So this will become important later. Okay, so you don't have to have current to create, EMF is self-sufficient, right? It may or may not carry current. And in this case, we want to get current. So this is V primary, voltage between these two. This is V secondary. So this is transformer's formula. Let's see, we're going to put it here. Transformer. And basically it looks like this. The voltage on the primary coil will be proportional to the number of turns in the primary coil. And the voltage on the secondary coil will be proportional to the number of turns in the secondary coil. So this is the consequence of Faraday-Lenz law. And this will be equal. So that's basically our formula. Like that. Okay. Now let's try to understand why we have N here. you can imagine that we have multiple sources of electricity. So each coil or each ring can be considered a separate source of electricity. So think about this as a separate, like a cell, right? So if we connect 3 cells like so, plus to minus, plus to minus, plus to minus, we end up adding voltages like this, right? So that's going to be giving us V total. And that's why in the EMF formula, you have this, obviously, delta phi over delta T, and then you have the N here. So each coil produces its own voltage, and then since all coils are connected in series, you get increased voltage. So if you have 500 turns, that's going to be 500 times voltage on a single turn. So from here, we have a question. Like if we solve this for the, if we solve it for V secondary, right? Let's say Vs is going to be equal to V on the primary over N over primary times N on the secondary. So suppose V on the primary is 10 volts, and then the number of turns in the primary coil is equal to, say, 20. Number of turns in the secondary coil is equal to, let's say, I don't know, 100 turns, right? What will be voltage on the secondary coil, in the secondary coil? Okay, please respond in the chat box. Daniel, are you participating or not? I didn't see any responses from you, Daniel. Oh, now I see. Okay, so 50 volts, right? So question then, we had 10 volts power source. Now we get 50 volts. Doesn't mean we like gain more power. We increase the amount of energy, or we produce energy out of nothing. Is that what it means? Obviously, the answer to this question is, well, some of you may be still thinking about perpetual motion, right? What's it called? I was just reading this in the morning. Free energy, free space energy, hidden vacuum energy, all kinds of ideas. So we can't produce energy out of nothing. That defies conservation of energy, right? So then, in order to understand this, we have to write the formula for the power. Electric power is I times V. So whatever power you have on the primary coil, you should have the same power on the secondary coil. Ideally, if you don't have any losses. So that's an ideal case, but you know this is not going to work already because we already have some energy dissipating into space, right, in form of radiation, electromagnetic radiation, a little bit of it. Some of this energy will be heating up the coils, the copper, the cores, this are the magnetic cores, iron cores. So they will heat up, and obviously this energy will be lost. So over here on the side of the IS, you will have some sort of coefficient, which stands for efficiency of a transformer. Efficiency of consumer like rated transformers, anywhere from 70 maybe to 80%. Transformers which are used like high-end transformers, large size transformers, may get more than 90% efficiency. However, in some cases, people ignore the fact that they have to force cool transformers so they don't overheat and melt down. And they may not include that energy expenditure, into the efficiency formula. So usually get less energy on the secondary coil. Any questions? Do you guys have any questions? No questions. Okay. No means no. What can I say? Let's move forward. Next slide. So, if you ever heard about the battle between two people, Tesla and Edison, right? Edison was the kind of person who would steal and cheat and everything to get what he wanted. And Tesla was working for him. Actually, he was hired to solve some problems that Edison could not solve. Edison was not educated like an engineer or anything. He kind of self-taught, kind of genius in a way, but also like evil genius. He's the guy who invented electric chair. He's the guy who suggested testing it to prove that DC is better than AC. It was tested on humans, prisoners, and that's how electric chair idea came along, to execute prisoners. Tesla was a kind of an honorable man, and when he was working for Edison, he worked for him on the promise that Edison made to pay him a certain amount of money, substantial amount of money, for solving a difficult engineering problem. When Tesla solved it, Edison said that he never promised to pay the money. It was kind of a joke. Tesla went on working for Westinghouse, I think, company. They successfully moved to generating and passing electricity over larger distances, greater distances, using AC. And Edison basically tried to bankrupt Westinghouse, and also he acquired patents or rights for Tesla's inventions. And basically he bankrupted Tesla, Nikola Tesla, right? And he died in poverty. Eventually, we're using what we're using AC, not DC. Edison's idea was to have, in every block of Manhattan, you would have a generator, which would be, one, noisy. Second, it would be producing a lot of fumes because it would be running coal or oil. So it'd be burning oil or coal to produce electricity. And since you can't conduct DC over long distances, because that will there will be a lot of losses, you would need a generator per block, per city block. Okay, that was his crazy idea, and obviously that failed. So what do we have? We have power that is generated somewhere near the water or some like power plant, right? So this will be like, let's say, hydropower plant. So this will be hydropower plant, right? So, and hydropower plant generates a lot of current, decent amount of voltage, but a lot of current, right? So what you want to do is you want to have means to transform this electricity. And basically what you do is you transform it using stepping up transformers. So over here we'll have the cascade of stepping up transformers and stepping up transformer has higher voltage on the secondary coil. On the secondary coil. So you will have a cascade of this stepping up transformers, right? Each one will raise the voltage to the higher voltage. Eventually, you will reach the point where electricity is conducted through those high voltage towers, right? Which you will see like between the cities. Like this can go for hundreds of kilometers. Maybe not hundreds, well, hundreds of kilometers, I guess, I don't know. And then eventually I bring it to the consumers. Consumers cannot use 100,000 or 500,000 volts, obviously. You have to have the cascade of stepping down transformers. So here you will have basically consumers. What's going on? Consumers, right? And what we have here is stepping down transformers. Stepping down transformers. So which will has lower voltage on this secondary coil. Somebody woke up. Okay, so let's see. Okay, let's just move it here. Okay. And this thing is called high voltage something. High voltage lines, I guess, I don't know. Okay, questions about this? Are you guys awake?
Yes.
Okay, Hugo is awake. Okay, more people are awake. So, yes?
Why is transporting higher voltages like more beneficial?
Very good question. So, electricity, I mean, the loss of electricity are proportional to the R, right? So, basically you have power is equal to V squared over R, right? Is it like that? Is it the formula?
Yeah.
Yeah. So the smaller the R, the more power you can transfer more power. Right? But you're limited in how much R can be. So how can you transform more power? You have to increase the voltage. But if you increase voltage, then you have to decrease the current. Another way you can write, so power is equal to I times V, right? If you lower the current, you want to increase the voltage to transform the same amount of power. And the current in turn depends on resistance, right? So voltage over R. So you have a lot of wire, a lot of resistance, the current will be quite small. So you want to keep the current small enough, but at the same time keep the voltage high enough. Make sense?
Yeah. Yeah, I just have a question.
Yeah.
In the first equation, P is equal to V over R, and it's something else. What's next to the V?
It should be squared. Is it right? Let me check.
Yeah, because it's IV. I is V over R.
I is equal to V over R, right? Oh yeah, right. So yeah, that's a square. Dragons.
C squared?
Yeah, this is squared, so this should be what? should be square. There you go. It's a little better. Okay, so even in this kind of system, right, we still lose from about 40 to 60% of electricity. It's lost due to the emission into the air, like radio waves, but most of it lost due to the heat. So when people pay for electricity that they use at home, they're paying for the electricity that they use at home, plus whatever losses the electric companies get due to the, like, between generating and then delivering to the consumers. Okay, so we have almost no time. I want to go with the last part of the homework from that worksheet. So question number 20 and question number 21, they're conceptual questions, and basically have to figure out the direction of the current in each one. So if you look at number 20, basically have the wireframe that looks like this, and we're interested in the amount of current, not in the amount, in the current, direction of the current in this, and this parts of the wireframe. Okay, what you have to understand is the flux is changing, and the rotation of this thing is this way. And based on that, you can figure out how the flux is changing, use Faraday-Lenz law, and figure out direction of the current. The second question, 21, basically it's the same question, except that you have the wireframe as seen from above, right? You have two poles, south and north, and basically you have to figure out, as this turns this way, which way would current be going on the top and the bottom parts of the wireframe. So these two are conceptual problems. Question 22 and 23 are computational. You have to find EMF. You have to understand that the sine and cosine functions have the range of +1 to -1, right? Which means area will change from +A to -A, considering that minus comes from the normal, right? So delta A basically is equal to 2A. Okay, you have to use that to figure out change in the area over time, and that will give you the EMF as you plug in the numbers. N's are given, the number terms are given. You have to figure out the T during which this change happens, and this happens over the half of the period. So you should recall how to find period from the cosine and sine function, sine function's argument. Okay, and that should be it. Okay, we're done. If you don't have any questions, I would like to wrap it up.